This lecture talks about a baseline survival model. It's called proportional hazard exponential regression. The exponential regression or a proportional hazard exponential regression is the simplest form and baseline regression of a parametric survival model. It assumes that the time to event, that is the response variable, follows an exponential distribution. So its probability density function, that is f of t, follows this form. Okay? Lambda multiplied by e raised to power negative lambda t. Here, lambda is the parameter, and it is assumed to be positive. Okay? And its corresponding survival function, uppercase s of t, is equal to 1 minus uppercase f of t, which equals e raised to power of lambda t. And that result can be computed from a function for the probability density function f of t. And if we take a ratio of these two functions, right? So lowercase f of t, which is the probability density function, in uppercase s of t, that is the survival function, then what we get is called hazard function, right? And it happens to be lambda if we take a ratio of these two functions that I just talked about. And here, we don't have any covariate. And if we apply this function onto data, then all subjects are going to have the same lambda. And all subjects are going to have the same survival curve and hazard rate curve. And if we add covariates to the model, that is, if we assume this hazard function varies with covariates, then we're going to have different lambda, subscript I, varying with different subjects, thus leading to different survival curves and hazard curves. Okay, here we have a very simple example for the proportional hazard exponential regression. And the model we talk about is what I call intercept-only model without any covariates. So in this case, let's assume the probability density function f of t is equal to 0.3 multiplied by the exponential function of negative 0.3x. Okay, so here x is time to event variable with lambda set to 0.3. So the parameter here is set to 0.3. Well, if that is our starting point, then its cumulative density function, that is uppercase f, is equal to 1 point the exponential function of negative 0.3x. Okay? And its survival function, which can be computed from lowercase f of t, is equal to the exponential function of negative 0.3x. And the hazard function is equal to a ratio of lowercase f of t, that is the probability density function of the time to event variable, over the survival function s of t. In this case, is 0.3, right? So hazard function is equal to lambda. Thus, we have a constant hazard rate. That is, at any given time point, individuals, the subjects, all subjects going to have the same hazard rate, and that hazard rate is constant across time. Below, we have a graph of this time to event variable, including the probability density, the cumulative probability distribution, the survival function. So here we have this survival function S of t, right? Given that the lambda is a constant 0.3. So here we can see that the survival function begins from 1, then decreases exponentially. And here is f of t, right? The probability density function for this time to event variable. And f of t roughly tells us, the proportion of people, roughly speaking, ballpark, not very precisely, the proportion of people dying at any given time point. And f of t, uppercase, is the cumulative of lowercase f of t. And if we take a ratio of s of t and f of t at any given time, well, here we get a constant hazard. So literally speaking, the danger of dying is constant across time. So this is a unrealistic assumption. And that's the reason why this model quite often, even after we add covariates, is used as a baseline model, very much like the Poisson regression for count response variables. Okay, so the quantitative interest in proportional hazard exponential regression is the hazard function. Okay? And the exponential regression model, PH, that is proportional hazard, PH exponential regression model is the simplest form of parametric survival model because it assumes that the baseline hazard is a constant. The baseline is a constant. So the hazard function is modeled like this, right? And here we have a baseline hazard. And then we have exponential function of x beta subtracting that intercepted term from it. So this x beta subscript -0 means that we don't include intercept and the unit column in this linear predictor. And then we use exponential function of beta 0. That is, we put the constant into the baseline hazard. Okay, and then the other part retains the same. And once we combine these two terms, we can obtain a constant term here. Okay, so the hazard function in this case is a positive number, and it is modeled using the exponential function.